So in the previous two parts, we've started implementing this Autograd system by first creating the variable scalar, right, as a custom class, which allows us then to define operations. And we have focused on addition and multiplication, right? And then once we do the Autograd system completely, you can then explore or experiment on this and try other operations. We've then, in the last video, kind of found a way to keep the history by just passing it in and storing references to the operations that result in the particular variable, and that then allows us to kind of visualize our operations in a graph way, in a computation graph, right? So you can see A and B, its addition leads to C, C and D, multiplication leads to E, which is what we have set up here. We have done A and B, A plus B is C, and then D, and then C times D is E. Okay. So now the last piece of the puzzle, let's implement the differentiation part, so the backpropagation part. First thing we're going to do is we're going to modify this and add a variable called gradient. We're going to initialize it to 0.0. And one small change I'm going to do here is I'm going to set the value to 0.0 by default. Okay. So what's next? Next, we need to implement a function called the backward function. So what I'm going to do is define a default backward, right? And I'm going to call it, right? And what that backward function is going to do is going to be a simple lambda function, right? It's a very nice, simple way of kind of defining a function like this inline. And it's just going to say none. So by default, nothing happens if you call it backward. So if you call it in a variable that does not have anything before it, or rather in this case, an object of scalar which does not have anything, nothing happens. But now what we can do is for the operation, where does the backward need to be called? So let's say you have E here. Now there's no point calling backward on A or B or D. There's nothing, for it to be passed back. But what you're saying is, let's say E is the end of the cycle. Now you want to differentiate and find the derivative of, say, E with respect to D, A, and B. So you want to call backward on E. And because it knows it's a multiplication operation, it's going to take the derivative of E with respect to D and with respect to C. Right? And that is going to be passed to C and D. So C and D also has those values. And then what you're going to do is now take the derivative of C with respect to A, and then chain the derivative of E with respect to C and push that. So that's kind of how the backward pass is working. We've covered the theory quite well in the first two kind of theory parts, right? Where we've covered the chain rule and building and differentiating a computation graph. So let's implement that. Where we're going to implement it is we're going to implement it here where we create, right, this add. So we're going to say here def, and we're going to define a backward. Let's say backward, right? And because it's defined here, it has access to out, it has access to other, right? And so what we're going to do is say now self dot gradient, right, is, and now what is it going to do? Well, it's going to say it's the addition operation. So if you differentiate the addition, right, let's say you have, C is A plus B. So self in this case is A. The derivative of A with respect to A, the A, right, is what, right? And what we are looking to do is chain that. So we want the derivative of A with respect to, we want dA, E dA. We're saying, well, by chain rule, it's dE dC times dC dA. Now dC dA, we're saying dC dE dC is already stored in C dot gradient, because when we say gradient here, it's the derivative with respect to the last value or the value we want to differentiate with respect to. So where we are back propagating from, it's with respect to that value. So in this case, C, right, which is just out, right? This out is the C for A plus B, right? Assume that's the operation. Because back propagation is coming from the next value, C should already have computed and should have stored its gradient with respect to it. We're assuming that, right? And so dE dC exists in C dot gradient, and dC dA is basically d of a plus b with respect to a, which as we know is 1. So it's basically going to be 1 times, right, and times out dot gradient. Now this seems a bit counterintuitive because you're going to say, well, I've just created out here, right? So how do you get out dot gradient? Well, the answer is it's not being called that way, right? We're creating this function here and using out dot gradient, but when this backward will be called, right, the gradient of out, which is c in this case, let's say, has already been computed, and then this is being called. So the value would already have been stored, right? That is why we're able to call this. Something to keep in mind. And so you can do the same thing now for other dot gradient, right? And it's 1.0 times out dot gradient, right? And so this out dot gradient here is the DCDA of the chain rule, right? Or rather the DEDC, so the derivative of the final value, in our case E, with respect to the out here, which is C. And then the 1.0 is the local derivative, right? It's DCDA, or in this case, DCDB, right? Okay. So we've got that. One more small piece, which is when you call the backward, you could have, more complicated loops or structures. So what you do is not just store the gradient, you accumulate the gradient. And so I'm going to write that here. Plus is to accumulate. Because if suppose A, you have E, and then you say F is A plus E, right? So another sensitivity of A with respect to F, let's say, comes from that operation. And so this will accumulate. So we now compute the gradient of self, right, and other. So in the operation of A plus B is C, self and other are A and B. We're assuming that C's gradient has already been computed a step above and has been stored there. We're now going to chain that here, right? And so that basically computes the gradient. Now, one more piece of the puzzle that we're going to implement right here. Now, there are two ways to do this. You could either, like we have done, create the whole graph and visualize it, then call the gradient from there. What I'm going to do is actually say, now that we've got this, we have stored the gradient of self and other. What do we do? Well, so what have we done? Let's say we're here and it's D and C, right? That would be in the multiplication operation. But let's say we're here and we are at D and C. So I've got DED and DEDC. Now I'm here. What do I want to do next? I want to call backward on this now, right? So that it moves further down the chain. So that's what we're going to do. We're going to say now, we're going to say self dot and other dot. And it's a backward with an underscore. And so it's going to assume, and actually let me call this underscore backward. Now, if this is a node that, is a leaf node, it's got D, for example, the backward does nothing. It's just none, right? On the other hand, if it's C, then the backward is defined, right? Because we have just defined the backward for addition. It's going to go and call that function, compute the derivatives for this. And then if there's a backward there, push it back. So we're going to define the backward here itself. And so that is the end of this backward function. And then what are we going to do? We're going to say, well, before we return out, we've created this function. We haven't assigned it. We're going to say out dot underscore backward is equal to underscore. So this is sometimes a bit tricky to understand because you're saying, well, I've just created out here. Where does the gradient show up from? The gradient hasn't been computed. But the trick is we're creating this here and we're assigning it to out, but the values, it's only going to be run in the backward pass, right? You're going to do the entire forward pass and then you're going to run this in the backward, by which time these values have been set up and your computational tree exists properly, and then this backward function. And so what we can do now is copy this, right? The backward, and we can apply that here as well for the multiplication. What's the difference? The difference is quite simple. For multiplication, right? The chain rule is the chain rule. but it sees a times b. So the derivative of, in this case, a times b with respect to a is b. Right? In this case, it's 1. So self dot gradient is what? So say self is a. In this case, it's b, right? So it's other dot value. And if it's other dot gradient, it's self dot value. Simple. And then you're chaining that with what has been passed from the value ahead. So out, which is what has been created, the gradient of that, it's assumed that's already been computed. And then this is being called, and so it does that. The rest of the steps are the same. So what that now allows us to do, let's go create this graph. Let's just rerun this. Right. Let me make one more modification. Let's now take this computational graph here. And what I'm going to do is say here, let's also add, apart from the label, let's add two more sets of values. Let's add node dot value and node dot gradient. Right? Okay. So let's rerun this now. Hopefully no errors. It's computing this. It is picking did I call backward? Um, okay, I used the function. It's not function, it's just assigning it. So that's my mistake. Don't use the brackets here, just going to call it, right? Okay. So we do that, okay. But p dot previous. Now what we can do here is we're going to call the back, right? And so we're going to say e dot backward, right? And let's run that. Doesn't show any errors. Let's reconstruct the graph and let's visualize it. And it has visualized it. Now there's one problem. The values are okay. 1 plus 2 is 3, 3 plus 4, 3 times 4 multiplication is 12. The gradients are all 0. Why is that? Answer is simple. I've called e dot backward, right? But what's the gradient of e? Right? The gradient of e has been set to 0. So when it does the chain rule, it's going to start here. It's set this value to 0. Now, when it's chaining, it might have a local derivative, but it's being multiplied by this value, right? Because we're doing out dot gradient. So the first operation that will be performed is the derivative here. E dot gradient is 0. So the derivatives here are computed, but it's chained with 0. So what are we going to do? We're going to say, well, e dot backward, and you pass in the derivative of the last value that you want to push back. Now, in this case, if you have, for example, it's a neural network and a loss function, you pass the derivative with respect to that. In this case, the gradient of E with respect to E, because you want the sensitivity with respect to E. You're saying I want the sensitivity with respect to the last value here. The gradient of E with respect to E is 1, right? So DE is 1. So let's rerun the backward, right? Okay, actually not this way. That's my mistake. It's E dot gradient is, right. Okay. So we've done that. We've set the value to 1 and then we rerun this. Now let's visualize the graph. So now this is 1. Now the derivative of E with respect to D is C, and the derivative of C with respect to D is D. So we've got that. There's nothing more to run here. So D is D. We want to push this back. So now we've got the value here of 4. The derivative we know locally is 1 when it's addition. So 4 is pushed back. And the derivative of E with respect to B is 4. And the derivative of E with respect to A is 4. So in a fairly simple manner, we have created this class called Scalar. And using the scalar object that we've created, which is a custom variable, we are now able to create a computational graph for addition and multiplication operations. We're able to visualize the graph and we're able to now do a differentiation. Now, that's kind of it, right? That's as simple as it goes. Now, how does this become more complicated? Well, you can add other operations. So add division, add subtraction, raising to the power of, and trigonometric operations, so sine, cosine, tan, the exponential function, and you get something that's a lot more functional. Right? Another piece of the puzzle In this case, I can only do A is scalar, B is scalar, C is A plus B. What if I want to do C is A plus 1 or A plus 2, right? It's not going to work, right? Because, well, it's going to check for its instance. And if it's not scalar, it's going to throw an error. What you can do now is modify this and say, well, what if I pass a value to it, right? What if I pass actually something that's a float? Well, I need to provision for that, right? To make sure that it still works. Similarly, what if actually I call the addition on a float? So actually, instead of A plus 2.0, I say 2.0 plus B. So this is a floating point. This is scalar. Again, the addition is not going to work. So you need to define for that as well. Now, those are more advanced pieces of the puzzle. I'm going to leave this here for now. And this kind of gives you or should give you a very good understanding of how Autograd works, right? And then, if required, we can go and upgrade this to allow for that. There's one more thing that we can upgrade it for, which we'll kind of look into in the future at some point, which is what if the operations are vector operations, right? So if you have a vectorized neural network, now if A is a vector and B is a vector, how does this work? And the basic principle is the same. You understand how to set up the operations, right? Only now what you can do is you'll have the corresponding vector gradients here and the vector values, how the operations matter. But hopefully this has given you a fairly good understanding, in a fairly simple fashion of how a different automatic differentiation system or an autograd system works and how the chain rule can be used to, differentiate these computations. Right? So that should kind of, help you understand both autograd and how, if you use this variable now and build a neural network, the back propagation would use this, right? And so that's how that would. So hopefully this is, given you an understanding. Stay tuned for the next one.